Assalamualaikum warahmatullahi wabarakatuh. Our group is group number 9 and my name is Ahmad Akram Asfar bin Lafad Ibrahimi. My number metric is CE230157. My second member is Hafzalham bin Muizzuddin. His number metric is CE230094. And my last member is Muhammad Hazmi bin Zainuddin and his number metric is CE230087. I want to explain about introduction. First, the basic component of a resistor, inductor, and capacitor are connected across a voltage source in an resistor, inductor, capacitor circuit. These components are all passive and linear in nature. Linear elements have a linear relationship between voltage and current, whereas passive components consume energy instead of producing it. Second, the resistor, inductor, and capacitor in a parallel resistor, inductor, capacitor circuit are connected in parallel across a voltage source. The series resistor, inductor, capacitor circuit and the parallel resistor, inductor, capacitor circuit are diametrically opposed. All components receive the same applied voltage and the supply current is divided. Next, since the current flowing in the resistor, inductor, and capacitor are not in phase with one another and cannot be added arithmetically, the total current drawn from the supply is equal to the vector sum of all the currents rather than the mathematical sum of the current flowing in each individual component. Typically, there are three methods for solving second-order circuit: overdamped, underdamped, and undamped. Depending on the values of angle and data, second-order learning is crucial to electronic engineering and will be applied in the workplace. By examining three potential outcomes from a qualitative perspective, we can gain an understanding of the complete richness of the natural response.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azmi bin Zainuddin. My metric number is CE2300X7. Today I will present about question 1. And we use under frequency omega equal to 1000. This is the circuit for overdamp. For the R1 is 20 ohm. For the critical damp, we use 10 ohm. And lastly is under damp, we use for R3 is 5 ohm. This is our circuit for question 1. Next, this is the circuit, the graph for the underdamped. This is the point. Okay, next is graph for critical damp. Then we take at this point. Next is overdamp. Graph for overdamp. And then we take this point. Okay, that's all for me. Thank you.
Explanation for question 2. And then this is the voltage state VT for the equation. For the VT this equation as circuit. Okay, and then for the IA, this is for IA. IA at the 5 ohm, between 5 ohm and 1 ohm. Okay, for the IB, is between for the 4 millifarad and 2.5 millifarad. Okay, for the IC is between from the 2.5 millifarad and 20 ohm. Okay, this is equation and this is the graph. You see that is the graph and this is the graph. What you get is 3.17 for the IC. For the IB, 73.42. For the IA, 9.89. For the voltage, this is
I want to explain about discussion. Three different types of natural response demonstrate how the respective magnitude of angle and delta zero affect how the circuit reach its steady state. First, over them. When we use is angle bigger than delta zero and the solution is real distinct root S1, S2. Second, other than when we use angle small over than delta zero and the solution is complete roots S1 equal to bracket S2. Last, critically them when we use angle equal to delta 0 and the solution is real equal roots S1 equal to S2. Next, the solution is the sum of final current IF equal to IS and the natural response IT nature bracket T, and the formula you can see at the slide. Then, a second order differential equation is required to solve for the voltage across or the current flowing through a component, which is the circuit will contain at least one resistor and the equivalent of two energy storage elements such as two capacitors, two inductors, or a capacitor and inductor. The usual approach to solving second order differential equation is to split the solution into two functions. F bracket S equal to Ft bracket S plus Fs bracket S. Ft bracket S is mean fraction solution, sometimes called the homogeneous solution. Next, for the Fs bracket S is mean steady state solution, sometimes called the particular solution. The steady state solution Fs bracket S is any function that you can find that is a solution to the full differential equation. Usually, it is found with a trial and error approach. The form of G bracket S will determine the form of Fs bracket S. Then, Ft bracket S is the solution to the homogeneous differential equation. And the formula, the next formula is d square 2 Ft bracket S multiplied Ts square 2 plus bracket A dft bracket S multiply ds plus bft bracket S equal to 0. Usually, there are two functions that satisfy the homogeneous equation ft1 and ft2. Example, sin S and cos S, or E equal to plus S and E equal to minus S. And so, the complete transition function is a linear combination of the two ft bracket S equal to A ft1 bracket S plus B ft2 bracket S. Finally, the two constants A and B are determined using the initial condition f bracket 0 and df bracket 0 multiplied ds. Using simulation software is much faster to analyze the circuit than calculation, as we use is to prove our calculation rather than build a circuit in real life. It doesn't harm us by doing error and also easy to adjust. We can access any parts in the circuit with a click of the mouse, which made debugging much faster. With this experience and implementation from this group assignment, we are evolving and progressing one step further to master this subject. Thank you.